Hello, welcome to episode 3 of Maths in an Empty Classroom with me, Mr. Southern. We're going to look now at example 3 of connected particles on an inclined plane. If you're wondering what happened to example 2, you are able to access this on the Ringwood School Learning Zone. I didn't go through it because there's a full worked example up there and it's basically the same as example 1 with the numbers changed. So I thought let's crack straight on to look at example 3. So here we have particle A of mass m kilograms. So straight away you can see m kilograms, we haven't been given the mass. Rests on a rough inclined plane making an angle theta to the horizontal where sine theta equals 3 over 5. We'll talk in a minute about how to deal with that. The coefficient of friction between A and the plane is 1/4. A is connected to a particle B of mass 2m by a light inextensible string which lies along a line of greatest slope of the plane and passes over a smooth fixed pulley at the top of the plane. B is hanging freely 1 metre above the horizontal plane and A is initially 2 metres from the pulley. So similar scenario to what we always have, with a bit of extra information and some more things that at this stage are unknown. So as we always do with mechanics, we start off by drawing a nice big diagram and labelling everything we know about the system. So here is our inclined plane. Let's just modify that so we can actually get the pulley into it. There we go. And we have the angle theta, because we didn't know the angle at this stage. We have a particle A just there. We've got the smooth fixed pulley at the top of the plane connected by the light inextensible string. And then we have the particle B hanging freely. Now we were told that particle A had a mass of m kilograms, particle B had a mass of 2m kilograms, and we were also told that initially particle A is 2 metres from the pulley itself. So I'm just going to draw on there a line that is 2 metres away from the pulley. Right, let's just have a little look back at it. Right, so particle A of mass m kilograms rests on a rough inclined plane making an angle theta to the horizontal where sine theta equals 3/5. The coefficient of friction between A and the plane is 1/4. Right, so let's just deal with a couple of those things then. We've got that the coefficient of friction is 1/4, so I'll write that over there. And we've also got that sine theta equals 3 over 5. Now what you don't want to do with that information is inverse sine find theta, because it's not really a very nice number, and it will just mean you've got more and more decimals to deal with in your calculations. What you need to do instead is to find the exact value of cos theta, because that's what we're going to use in our calculations. And the way to do that is just to draw out a very quick triangle, right angle triangle with an angle of theta. Now if sine theta is 3 over 5 and sine is opposite over hypotenuse, it means you have an opposite of 3 and a hypotenuse of 5, which using Pythagoras means that your adjacent must be 4, and therefore cos theta using adjacent over hypotenuse must equal 4/5. If you do enough mechanics, that's the kind of thing that you will just be able to see and remember rather than having to draw out that triangle every single time. Right, quick glance back at the question. A is connected to a particle B of mass 2m kilograms by a light and extensible string. We've done all that. B is hanging freely 1 metre above a horizontal plane and A is initially 2 metres from the pulley. So let's get that onto our diagram, the fact that B is 1 metre above the ground initially. And then what we need to find out is what way is the system moving, because as I mentioned before, that is going to determine the direction of friction, which is very, very important. So when the system is released from rest with the string taut, A moves up the plane. Right. So A moves up the plane. So let's get our acceleration arrows on here for A moving up the plane. And if A is moving up the plane, that means that B must be moving down the plane. So we'll label that on here. So I've now got the initial diagram set up. What I'm going to do now is label all the forces that are acting on this system. Starting with the weight of A acting straight down. Now I don't know the mass of A other than it's M, so I just have to label this as mg, where m at this stage is the unknown mass. Now remember, this weight is acting in a direction that isn't parallel or perpendicular to the plane that A is on. So I'm going to draw my dashed line in perpendicular to the plane that A is on, because I know that doing that creates the same angle theta here as I've got here. And while I'm there, I'm going to resolve that weight into its parallel and perpendicular components, because the weight down the slope is the bit that people always forget to do. So perpendicular to the slope, I have mg cos theta, and parallel to the slope, acting down the plane, mg sine theta. And these are the components of the weight of A. We also have a reaction force acting on A perpendicular to the slope. We have a tension force that is acting on A to pull it up the slope. We have an equal and opposite tension in the pulley, in the string I should say, sorry, acting on the pulley downwards like so. And because we now know that A is moving up the plane, friction will be opposing the direction of motion, so friction will be acting down the plane. I can draw that on in that direction, and they are all the forces acting on particle A. So now let's look at the forces acting on particle B. We've got its weight directly downwards, which is mass times gravity, so 2 mg. We have a tension force in the string acting on B going upwards, and we have the same tension force acting on the pulley going downwards. And as mentioned before, all four of these tensions are the same magnitude, same value, same number. Okay. Right, so let's now have a look at what we're being asked to do in the question. It's asked for the initial acceleration of A. So what we're used to doing by now, let's wait for it to respond. There we go. Right, so part A. I'm after the initial acceleration. As always, I begin by resolving perpendicular to the plane. So resolve perpendicular to the plane. And what I have going on here, again, I'll get my ruler like I did before, anything acting perpendicular to the plane. And I've got those two forces there. I've got normal reaction force, and I've got mg cos theta, which is the perpendicular component of the weight of A. And I know that those two things must be equal, because A is sliding along the plane, it's not moving up or down. So mg cos theta. Now at this stage I know that cos theta is 4/5, because I worked that out earlier. So what I'm actually going to write is that the reaction force is 4/5 mg. You could write 0.8 mg if decimals are your preference. The purpose of doing that was to find out friction. So using the fact that friction is mu times r. Friction is 1/4, which is our coefficient of friction that we were told in the question, times by 4/5 mg, which works out rather beautifully to be 1/5 mg. So that is the frictional force acting on A. Now we've done that, we're going to resolve parallel to the plane. Using that resultant force is mass times acceleration. Resolving in the direction of motion, which is upwards. Look in here, any forces acting parallel to the plane on A I'm going to consider. So T is pulling it up, friction is pulling it back, and look, that weight component down the slope that everyone always forgets, mg sine theta. So my resultant force equation for particle A, T minus friction minus mg sine theta equals mass times acceleration. Now I know quite a lot of this as values in terms of m and g, so I can put that into it now. I know that friction is 1/5 mg, so I'm going to put that in. I also know that sine theta is 3/5 because I was told it in the question, so I'm not going to write mg sine theta, I'm going to write 3/5 mg, replacing sine theta with 3/5, and that equals mass times acceleration. Simplifying that, I have T minus 4/5 mg equals ma. I'm going to draw a blue box around that because that is the first of my simultaneous equations that I'm going to use to solve to find the value of A. The other one that I'm going to use is I'm going to resolve for particle B. Again, using resultant force equals mass times acceleration. And looking at particle B, there's only two forces acting directly on B. 2mg going down, T going up. So the resultant force equation for B is 2mg minus T equals 2ma. Now that's important, mass times acceleration. The mass of B is 2m, so it's 2ma. Okay? That one there was ma because the mass of A was m. The mass of B is 2m. It's very, very important that we get that bit right because that will affect solving our simultaneous equations. And that's the second one. So what we're going to move on to do now is we're going to solve those two equations simultaneously. So we've got T minus 4/5 mg equals ma, 2mg minus T equals 2ma. And as before, if we add those two equations, it cancels out the tension. 2mg minus 4/5 mg is going to be 6/5 mg, and ma plus 2ma is 3ma. Now, the bonus here is the m's will cancel out because they're the same value, and then dividing by 3, we get that the acceleration is 2/5 g, and 2/5 g, working out 2/5 of 9.8 is 3.92 ms to negative 2, and that is the solution to part A. Right. Part B then is saying the time that elapses before B hits the horizontal plane. So, B is going to hit the horizontal plane. Went the wrong way there you go. B needs to travel 1 metre to hit the horizontal plane. So this is a SUVAT question. And the reason that I know that it's a SUVAT equation is that the acceleration is constant. You can only use SUVAT when the acceleration is constant. So part B, we're going to use SUVAT. And we know that S is 1 because that's the distance that B has to travel before it hits the ground. We know that U is 0 because the system initially started at rest. And we've now calculated that A, the acceleration, is 3.92. And we want to know the time taken. So we need our SUVAT equation that's got S, U, A and T in it. So S equals UT plus a half AT squared. These are in the formula book, which I think is absolutely disgraceful. I think you should be learning them because if you learn them, you become fluent in their use rather than having to look them up every single time you use them, costing yourself time and losing your train of thought of how you're actually even doing the question in the first place. So S is 1, U is 0, so 0 times T, so we've got a half times by 3.92 times by T squared. So 1 equals 1.96 T squared. I'm going to divide by 1.96 and square root. Now, calculator's gone over there. No, it hasn't, it's gone behind the camera, bear with. I think it's important there's a real life element to this. It doesn't seem too staged, so leaving my calculator somewhere random in the room is obviously part of that. So square root that, you come out rather beautifully with T is exactly 5/7. Technically it's plus or minus because we're square rooting. Of course we're not going to worry about the negative because it's time. So that is part B. So that is the time taken for B to hit the ground. Part C, the distance A moves up the plane. What we've got to consider now is what happens to A when B hits the ground. Well, I'm going to draw out a new system for this. Because what will happen to A when B hits the ground is that its acceleration will change. And the reason that its acceleration will change is that if B hits the ground, the string is going to become slack, which means there's no more tension. So there's now no more force pulling A up the slope because the string that was doing that has now become slack and is not exerting any force causing A to move up the plane. So the only forces we have now to consider are the frictional force and the one that everyone always forgets, the weight component down the slope. So we've still got that mg we've still got those components. The one that I'm interested in, because it's acting parallel to the plane, is that one there, which is mg sine theta. So for A, we have a new resultant force equation. So resultant force equals mass times acceleration. What we have is, we don't have T anymore. So if I go back to what we did in part A, this was our equation of motion for A. What's happened now is, because B's hit the floor and the string's become slack, we've no more tension, and that's what we're left with. So I'm going to go with that. We're going to go with minus friction, minus mg sine theta, equals ma. They're both negative because A is still moving up the plane, so resolving in the direction of motion, friction and weight are acting down, they're acting against that, so it's opposite. they haven't changed in magnitude. So the frictional force is still 1/5 mg, and the weight component is still 3/5 mg, because sine theta is 3/5, that hasn't changed. So we now have negative 4/5 mg equals ma. We can cancel the m's, and we can say that a is negative 4/5 g, which means that a is negative 7.84. So once B hits the ground, A will now decelerate. We should be happy with that answer coming out negative, because we think, okay, well, what's going to happen if there's no more force pulling it up? Well, it's slowing down. So it must have a negative acceleration, it's decelerating. And what we now want to ask is, how far does A travel before it comes to rest? At the moment, we don't have enough information to answer that question, because what we need to know is, what speed was A doing at the point when B hit the floor? So we're now going to calculate the speed of A when B hit the floor. And this is a Suvat scenario again. We know that S is 1, because B had to go 1 metre down to hit the floor. We know that the acceleration during that stage of the motion was 3.92. We know that the initial speed was 0, because the system started at rest. And we know, because we calculated in part B, that it took 5/7 of a second for B to hit the floor. What that means is that I can use V equals U plus AT. So V is 0 plus 3.92 times 5/7, which means that V is 2.8. So, when B hits the ground, A is travelling at 2.8 metres per second, at which point it starts to decelerate. It has acceleration negative 7.84. So what now happens is, V becomes U. Our final velocity now is 0, because we want to know when A comes to rest, how far have we gone. Our acceleration is negative 7.84, and we want to know the distance travelled. So we're going to use V squared equals U squared plus 2AS. So 0 squared equals 2.8 squared plus 2 times by negative 7.84 times by S. 2.8 squared is 7.84. 2 lots of 7.84 is 15.68 minus 15.68 S, and S comes out rather beautifully as 0.5 metres. Pause, check the question. Question says, the distance A moves up the plane. That's not what you've worked out. You've worked out how much further A travelled up the plane after B hit the ground. If B had travelled 1 metre down, A must have travelled 1 metre up the plane, so therefore the total distance that A moved must be the 1 metre it had already travelled plus the 0.5 extra, which means that overall A travelled a distance of 1.5 metres. Lots of work, but lots of marks. Take your time, be accurate, and consider all the things that you needed to know in part C. You needed the new acceleration for A after B hit the floor. You needed to know the speed that A was going when B hit the floor, because in the new phase of motion, when you had a new acceleration, you needed your initial speed to be the speed that A was doing when B hit the ground. Once we knew all those things, we could work out the extra distance it travelled before it came to rest, and then total distance travelled. The 1 metre it had gone before B hit the floor, plus the extra 0.5 metres it did before it came to a stop. Thank you very much.